To have Professor Nadya Mason from University of Illinois Champaign here today. She received her bachelor degree from Harvard and her doctorate from Stanford University under supervision of Anne Capitunic. And then she joined University of Illinois Urbana-Champaign after a postdoc as a junior fellow at Harvard University. She actually indeed worked as a postdoc with, I guess, Charlie Marcus and Mike Tinkham. We had Charlie last week, so I guess the topic is familiar. So she has done many interesting research. Among those are mostly interesting problems in how electrons behave in low-dimensional and correlated systems. So hopefully today we will hear about this superconductivity story that is very interesting. So she's now currently the chair of, I guess, APS Committee for Minorities. She has many awards, including Edward Boucher Award from APS, Maria Gilbert-Meyer Award, Woodrow Wilson Career Enhancement Fellow, Diverse Magazine Emerging Scholar, and many others. So it's a great pleasure to have Nadya here, and please join me to asking questions.
Great, thank you. I love coming back to New York. I was born in the city. I still have close family here. And I was here not very long ago talking about a totally different topic on topological materials. And so today I'm talking about superconductors, and there'll be one slide on topological things at the end just to connect everything. Is it too dark? You guys aren't going to fall asleep. I'll turn it up a little bit. I know. I do. I always worry, especially it's late in the day. Wait, did you turn it off all the way?
No. You want to do it?
Okay, here.
Dimmer? Yeah. Okay.
Yeah. Okay. How about that? I can see it. Okay. Good. So, so today I'm talking about controlling dissipation in superconductors. The purpose of this title is to use the term oxymoron. No one ever uses that anymore. It's a good phrase. And this oxymoron leads to new superconducting phases and transitions. And it's oxymoron because generally we think of metals as something that are resistive and have dissipation, and then superconductors are things that are not resistive and have no dissipation. And so controlling dissipation in superconductors seems like it doesn't really make sense because they should be dissipation free. But what I'll talk about is how if you actually look at sources of dissipation in superconductors, and I'll talk about two sources, then you actually get a better understanding and even control of superconducting states and how they lose energy. So today I'll talk about two types of dissipation in superconductors. They're both based on the same system of superconducting islands on metallic substrates. But I'll first talk about how in these superconducting normal metal island arrays, we see finite resistance superconducting phases, which is something pretty unusual. And then I'll talk about in these arrays, we also look at vortex interactions, so put on a magnetic field and pin vortices in an array between the islands, and then use that to control another source of dissipation, which is moving vortices, and find new types of dissipative transitions in that case. Okay, so we're talking about metals and superconductors. So I'll start with a thing that's even better known, which is metals. We all know metals. There's bulk metal, there's metallic wire, all sorts of metals. If you put a metal as a resistor into a little circuit and put a voltage across it, you measure a current, right? V equals IR. The power dissipated here is I squared R. Okay, so metals dissipate energy as I squared R generally. And usually this is good if you have a heater and a little space heater at home, which we need a lot in Illinois, which actually has the same weather as New York. I want to clarify that. Everyone always tells me it must be colder in Illinois, and I know that I have family in New York, and I can tell you it's exactly the same. It's not colder. So it's all the same. We all need space heaters. Okay, so if you want to dissipate energy as heat, it's great to have a resistive metal or something like that. But if you have something like a computer chip, then you don't want to dissipate energy as heat. And this is a huge problem these days. The amount of energy that's dissipated on computer chips and in power lines and in wires is enormous. And just to give an example of that, one Pentium chip has about 30 miles of interconnects, right? And this is not, I'm not talking about like the metal and transistors and everything else, just the interconnects alone end to end would be 30 miles long, okay? And so these things dissipate, just the interconnects dissipate about 25 watts. And that's a lot of energy if you think of how many chips are around and how small they are and what's going on here. And so if anyone's ever seen a supercomputer room, everyone see pictures of where supercomputers are? It's just kind of boring rooms and you see boxes in there. And that's not the most interesting part, because if you go underneath where the building is, there's huge water towers and water cooling systems that are like, 5-foot wide water pipes leading to everything to cool it down. They have to have separate structures outside. It's the infrastructure for cooling that's really the most impressive part of it, because this is the biggest problem. How do you cool these supercomputers? So losing energy due to metals is a major problem overall. Okay, so enter superconductors. Right? Superconductors are the opposite of this. They don't dissipate energy at all. So superconductivity was discovered more than 100 years ago by Colloquium. He discovered how to liquefy helium, just make the coldest liquid in the world at that time at 4 Kelvin. And once he discovered how to do that, he put lots of different materials at that cold temperature, right? So he liquefied helium and then dunked a ton of things into the helium and saw what happened. And when he put in mercury, actually I think his lab tech put in mercury while he was out to dinner, but regardless, when they put mercury in there, he found that the resistance lowered as he lowered the temperature, like most metals, but then miraculously, at some critical temperature, the resistance suddenly dropped to 0, right? Which is actually, even when I see it now on a data curve, it's still kind of amazing to see something drop so precipitously like that, really to 0 resistance. And so, a non-superconducting metal should have a finite resistance as you go to low temperature, and a superconductor drops to 0 resistance at low temperature. And of course, there's clearly, differentiation between metals and superconductors in this case as you approach TC or 0 temperature. Okay, so superconductivity. Why does this occur? Why is it not just like a normal metal? Well, superconductivity occurs because of interactions between electrons. They pair up. Their pairing is mediated by the lattice, and so it's an attractive interaction. And because it's mediated by the lattice over large length scales, the pairs can move basically independent of disorder that might appear in the rest of the system, which means that they don't scatter, which means they move without losing energy. It's dissipationless. It's actually a quantum phenomena. These pairs condense into a real quantum ground state, which is characterized by an amplitude and a phase. And these are Cooper pairs, opposite spin electrons. Okay, so when I first heard about superconductivity, probably like many of you, it seemed like a really esoteric phenomenon, things that condense at very low temperatures. They have to pair up, they have to move without resistance. It seemed kind of crazy that nature would do that. It turns out it's incredibly common. Almost every basic element superconducts at some temperature, which tells you how crazy nature is, really. So here's all the materials that superconduct. You can see their TCs vary. Okay, I don't know why they included this because it has a 0 TC, but those don't superconduct. But even these guys superconduct at pretty low, these are Kelvin, pretty low temperatures. Almost all of the elements superconduct at some temperature. We're going to talk about niobium, which superconducts at 9.5 Kelvin. Aluminum is also popular at 1.2 Kelvin. These are all pretty low temperatures. Then there's the alloys, things like niobium-3 tin, which is used in MRI magnets. That superconducts at higher temperatures, but also can withstand very high magnetic fields, so it's good for magnet wire. And then there are the high temperature superconductors, things like yttrium YBCO and visco. These superconduct at 90 Kelvin, which is important because it's above the temperature of liquid nitrogen. And liquid nitrogen is much less expensive than liquid helium. Liquid helium costs something like...
Scotch? No.
Like scotch, you said? I think that's right. So that is it's exactly the analogy. So liquid helium costs as much as a fine scotch, and liquid nitrogen costs as much as milk. So when you get a 60-liter dewar of helium, just think of that as scotch. That's how valuable it is, right? Even that much milk is valuable, but not quite in the same way. So it's incredibly expensive. Nitrogen is easier, so having things that superconduct above nitrogen temperatures is great, but it's not room temperature, right? So superconductors have lots of applications, of course, because they have no resistance. They're really interesting materials. They're used as low volume wires in places like New York, where you have, as I was walking here today, I saw someone, they opened up the street and showed all the power lines and pipes and stuff underneath, and it's an incredible maze if you ever stop and look at that. So of course, in places where you have high density lines, you maybe can't fit in many more power lines. It might be worthwhile to use superconducting lines and things like these in wind turbines. Of course, for MRI magnets, accelerators, there's the ever elusive levitating train. When I was in grad school, people said that this was being built somewhere outside Tokyo. If you ask anyone now, they'll say it's being built somewhere outside Tokyo. It seems to never happen, but it's possible. That's how you make a levitating train. You have a magnetic levitation there, flywheels. Sensitive detectors are made out of superconductors. Single photon detectors can be made by putting a material right at the superconducting transition point. So if it's just below the superconducting transition, you can imagine a single photon coming in and exciting it just above the transition. So you get a big change in resistance for a very small input of energy. So the most sensitive detectors are made of superconducting materials. And of course, quantum computing elements, qubits, Josephson junction, superconducting qubits are among the most popular devices for potential quantum computers. Well, I'll leave it at that. I'll let Charlie talk about topological. Okay, but superconducting qubits are what Google and IBM and people are using for their quest for not to say quantum supremacy. I hate that term for quantumness for making a better quantum computer. So those are the devices that are being used. I feel like we shouldn't use the term quantum supremacy. Anyway, so you would think with all these applications and this lack of dissipation, superconductors would be used in everything, and they seem to be promised all the time. If you write a grant proposal, you promise to use them in everything. But of course, they're still need to be used at relatively low temperatures. Even nitrogen temperatures are still relatively low, and high TC materials are ceramics and hard to manipulate, and so we're still limited in our applications of superconductivity by the fact that they still have a relatively low TC. You can see here, this is the temperature, the transition temperature is a function of year, and here's the elements around 1911, and then it steadily goes up, and then there's this big jump in the 80s when high TC materials were discovered, and another jump with some pressure materials. The mercury-based compound went all the way up to about 140, 150 Kelvin. But you can see this is around 1990, and there's been no progress in TC since then. This ended in 2010, but it's still that would just be more empty space, basically. Right? So who needs that? So there's been no progress in increasing TC. And the interesting thing about that is that, as far as I know, there's no fundamental physical reason that we can't have a room temperature superconductor. Right? There's no law of physics. There's no fundamental theory that anyone's ever told me, that I've ever heard of, that says this is a reason you can't have a room temperature superconductor. And as we know from physics, if something is possible, right, then it should exist. Right? If there's not a law against it, we should be able to find it. And so I think the reason that we don't have a higher temperature superconductor is really our limited understanding of superconductivity even today. And this is because these are complicated materials, especially the high TC materials are very complex. This is a phase diagram, a typical phase diagram of the transition of temperature as a function of doping of a high TC material. And you can see there's a superconducting phase, but then around it is a metallic phase, and then another metallic phase, but in this case a strange metal, or even a very strange metal. And then here's a region that has what looks like a gap, but it's not superconducting, and an insulator that's not an insulator, it's a messy insulator, and then they throw in a ferromagnet, anti-ferromagnet, just for fun. Okay, so these are complicated systems that are still, I think, people are still trying to understand things like the nature of the pseudogap, what the strange metal is, whether there's phase separation in these things, which it looks like, and what the role of magnetism is. So there's still a lot to understand, I think, in terms of superconductors in general. And even beyond that, even if we just put aside high TC superconductors and say, okay, what happens to a superconductor in general as we make it lower dimensioned, right? As we change it to 1 dimension or 2 dimensions? It turns out even then, it's complicated. And this is because superconductivity requires long-range phase coherence, but if you have a 1D wire, any small fluctuation will destroy your coherence. Okay, so a single fluctuation in a 1D system will destroy phase coherence, so you should not have true long-range superconductivity in a real 1D system. Okay, then what about 2D? it turns out that in 2D is the lower limit for superconductivity. You can have phase fluctuations, but they kind of die out as power laws. And so you should have not true long-range order in 2D, but long-range order that decays as a power law in 2D. So you can see superconductivity just not over infinite scales in a 2D system. And actually, this was what the Nobel Prize was awarded for in 2016. This prize was for topology, for discovery of topological phases. But if you actually read the award for Koslitz and Fowlis especially, it's about them overturning the current theory that superconductivity could not occur in thin layers, and they demonstrated the mechanism of 2D superconductivity, which was a topological system of vortices in that case. So, or vortices are topological objects, so looking at vortices in a thin film superconductor. So interestingly, even though this sort of laid the groundwork for all future studies of topological behavior, it was really about how you could get superconductivity in a 2D system and what the mechanism was. So it's complicated. And they had a phase diagram here showing how, as a function of magnetic field and temperature and disorder, you have different sorts of vortex phases and phase transitions in superconductors. Okay, so one of the reasons that this Koslitz-Fowlis type phase transition was especially interesting is because another thing about two-dimensional systems is that it's been predicted that in 2D, you can have this kind of quasi-long-range superconducting state, and you can have an insulating state, but you can't theoretically have a metallic state as you approach zero temperature. Right, so 2 dimensions is even more complicated. Okay, and this is this famous scaling theory of localization, which says basically, as you lower the temperature, if you have a 2-dimensional metal, as you lower the temperature, any tiny amount of disorder will basically track the wave functions and prevent them and keep them localized. And so you end up in a localized state rather than a state where electrons can flow. So in theory, as you approach zero temperature, you should have a localized or insulating state in a 2D system. You should not approach a metallic state in 2D. And this is great because it's a theory that can be tested, right? So then you test a bunch of materials and see what happened as you approach zero temperature. And in fact, what was found is that a lot of systems had metallic states as they approached zero temperature, right? So metallic states have been seen in superconductors, in semiconductor heterostructures. In fact, the APS medal this year was given to Miriam Sarachik, who did her work on looking at metallic states in 2D semiconductors. This is what she was awarded this prize for. It's the biggest APS prize given. So understanding these metallic states in 2D has been, again, a kind of ongoing quest to see, what the cause is. And it's still relatively not well understood. It's not well understood. Right? And in fact, this is data that I took from my own thesis work. It was on a thin film superconductor, amorphous molygermanium. There's resistance versus temperature. And you can see that as a function of magnetic field, at low fields, it basically goes to zero resistance. It superconducts. And at high fields, it's a weak insulator. But as you go in between, the resistance sort of drops and then flattens out. Okay, even here. So you see the resistance dropping and then seeming to flatten, which means it's not approaching zero. It seems to be approaching some finite resistance state. And for me, this is what got me really interested in this topic to begin with. And for graduate students out there, if you depending on how you feel about your thesis project, I was ambivalent about my thesis project when I finished it. But years later, I find myself coming back to it. It turns out it's a thing I always know best. So beware, whatever you work on now is a thing you'll know best for the rest of your lives. Right? You're kind of stuck with it in your heart. So this always stuck with me. What caused this state, and is it related to some of these other anomalous metallic states that are found in other systems, like the the metallic state in high TC materials, for example. There's me in graduate school with my fridge. Okay. So when we first did this work, we recognized that there is this what we call a superconducting metallic state, or a metallic superconducting state, whatever you want to call it. And so we wrote some papers on it, and we proposed that the metallic state was caused by some dissipation in the system. So we came up with a phase diagram, and the phase diagram said that there's a superconductor on one side and an insulator on the other, and then as you add dissipation, you get a metal. Okay, and on the one hand, it's it looks like a phase diagram. On the other hand, if you think about this carefully, what we're saying is that you get dissipation from dissipation. And it's kind of a circular reasoning in here, that there's dissipation in there, then it causes a dissipative state, and we didn't really say what the dissipation was. And this really bothered me for a long time. So it introduced the idea that there's something dissipative in a superconductor, but we didn't know what it was, or what caused it, or what the mechanism was. Now, there were some theories. And the theories, by the end of the day, there's over many years, they sort of converged on this idea that the dissipation was likely due to phase separation in the system. Right? So even if you think you have a homogeneous 2D superconductor, at some point it breaks up into different regions of superconducting, and non-superconducting regions. And then this combination of superconductor and metal regions can create this sort of local superconducting puddle network, which can lead to a metal. Okay, so it's this puddle behavior. So there are a lot of theories about these having regions of superconductor and regions of normal metal in this system, which could lead to this kind of dissipative superconducting state. Now, these were theories that talked about, phase separation in a superconductor, but I think this is even more general. It turns out that this sort of microscopic phase separation happens generally for low-dimensional systems. Okay? So in general, if you have a 2D system and it interacts with anything, right, a substrate, a surface, the air, right, it leads to little regions that are different, right, have different charges, have different strain, have some differences. And as you lower the temperature on a 2D system, which again is fragile to perturbations, it will tend to break up into regions that have different properties. And I feel like people seem to rediscover this every generation with every new material that comes out. So people saw this in quantum Hall systems. Microscopic inhomogeneities led to the phase separation to Hall and non-Hall regions. In graphene, they discovered these electron hole puddles. In 2D systems, this was a 2D complex oxide system where they found phase separation. Here's topological insulators, where people found phase separation due to these microscopic disorders. So I think that it's very, very common for 2D systems or low-dimensional systems to break up into different phases. And then the question is, so what does this result in, right? How do you get a correlated phase out of a phase-separated system? What is the mechanism, and what new states does that lead to? Okay, so we use superconductors as our model system, and to understand this influence of dissipation, we really want to make something controlled, like add dissipation in a controlled way to a superconductor, and then see if it leads to a metallic state. So we want to take like two superconducting pairs and put in something like a scatterer and see, okay, that leads to a metal. Now, of course, we can't separate pairs. That's really hard to do, and if you did that, you'd kill superconductivity. So we did the next best thing, which was we took superconducting islands and separated those with a metal where we could control the amount of metal between the islands, and then we wanted to see how that influenced the superconducting state. So here we have, top view, two islands on a metal, and you see I put them as different phases, because if they're not coupled together, they have different phases. From the side view, it's two superconducting islands on top of a metal. Okay, so in this case, a supercurrent flows between the islands if the islands are phase coherent, meaning that if they're phase coherent, they have the same phase, you get a supercurrent flowing. If they don't have the same phase, you don't get a supercurrent. Okay, so how do they get the same phase if they're on a metal? The metal has to be phase coherent itself, right? So these two islands are phase coherent up to a distance where the metal between them is phase coherent, and that distance is given by the normal metal phase coherence length, which is related to the resistance of the metal and inversely related to the temperature. So that means that if I have two superconducting islands and I lower the temperature to 0, for example, then these two should be coupled over even an infinite distance. Right? So as I lower the temperature, the distance over which the islands get coupled gets longer and longer and longer. And then I can couple these and see superconductivity between them. Okay, so then we want to make islands like this that are separated by some distance, lower the temperature, have them become phase coherent, and then change the distance at which they're separated and see how that affects the metal and the resistive state. Okay? So this is an actual AFM of the devices that we made. These are niobium islands on top of gold. And niobium superconducting, the gold is not until they're coupled over some distance, and then we drew in the arrows to represent phase. There's one on there. Okay, so we use these systems to control their interactions, and look at the phenomena that emerge in that case. Someone at some point told me they look like hamburgers.
Yeah.
They're superconductors, not hamburgers. And in fact, at one point I showed this picture and someone said something like, "Can you tell me about the inhomogeneity in the hamburgers?" And I was like, "Oh, are they parsley?" And I was like, "No, I meant the superconductors." So anyway, talk should never be too close to lunch or dinner time. Okay, so we're talking about coupled superconducting islands. And I also want to mention that this is not a new idea. Basically, I'm making what's called a Josephson junction. A Josephson junction is any two superconductors which are connected by some weak link. A weak link means it's not superconducting, right? That there's something that is not as superconducting between them. That can be a metal, that can be an insulator, that can be a thinner strip of superconductor. And actually, Josephson junction arrays have been around for a long time too. And again, for students out there, I should mention that when I first started working on this, one of my colleagues, whom I love, and we have a really good relationship, but this colleague said to me, "Don't bother working on this. I've done all this before. Everyone's already done this 30 years ago." And so everyone will hear this at some point in their lives. And the correct thing to do in that case is to listen and then ignore. Because, you know, when you look at things 30 years later, it's often with a new perspective, and often with new techniques even. In our case, we had new fabrication techniques which allowed us to make things a lot smaller and coupled on a very different scale. We were also looking at things like metallic states, which was not something that people had looked at before. Right? So it turns out there are new things to study, even with just a new perspective. Right? So it's worth thinking about your own ideas, even if people have looked at it before. Okay. For people who don't do lithography, we make these lithographically. Here's a very quick animation of this. We start with a silicon oxide substrate. We spin on a photosensitive material. We expose that material to light and then develop it, in which case the photosensitive material comes off and we develop it, and we're left with a pattern in the shape that we want it. This is our 4-point measurement pattern. In this case, we then deposit gold. And then the photosensitive material lifts off an acetone. We put the whole thing in acetone, and it breaks off here, and breaks off here, and leaves just our pattern behind. Okay? And then we do the same thing with the holes. We put on an electron beam sensitive material, and then use magnets in the electron beam lithography system to drive the beam around with a shutter and expose just where we want it. So we make all these holes across our system, and then we develop that. We develop that, deposit niobium, and then lift off again, and we're left with our 4-point measurement pattern covered with holes. It's a long story about why we use niobium, but we can evaporate niobium. It lifts off really nicely. It's why we use it. And also it works above 1 Kelvin, which means we can measure it very quickly. That's how you often choose materials for convenience. And also we wanted simple materials here for a model system. So here's what it looks like. There's another AFM image of the niobium holes on the gold substrate is our 4-point measurement. And because we do everything with lithography, it's all tunable. We can tune the island size, the island spacing, all the properties, the array configuration, and really start studying and parameters that are due to these metallic states and vortex dynamics, as I'll mention. Also to note some of the important parameters of our system. The niobium is very thick and the gold is very thin, and we've done measurements and other things to show that we're not decreasing the transition temperature of niobium because of the gold, which can happen if they're relatively thick or thin compared to each other. The island diameter is 260 nanometers. The superconducting coherence length is 27 nanometers. So the diameter of the islands is much bigger than the coherence length of niobium. It should be fully superconducting. And the normal metal coherence length is 270 over root T nanometers. And so at 10 Kelvin, this thing should be at 10 Kelvin, the island should be coupled at around 100 nanometer spacing. Okay, so when the niobium goes superconducting, if the islands are closer than 100 nanometers, they should immediately couple. Otherwise, we have to lower the temperature before they can couple. Okay, so the first thing we did is make different substrates with just different island spacings on them. We did triangular arrays so we could increase the spacing without changing any other parameters in the system. We made one chip, and each chip had 6 different spacings on it. Everything else was identical. This is an optical image of our system. Again, we just put a current across it and measure the voltage using a lock-in measurement. And we do all this at either somewhere between 1.6 and 15 millikelvin. And this is the typical data that we saw. This is resistance versus temperature for different island spacings. And so you can see that for the very closely spaced islands, we get one transition. These are close spaced by 90 nanometers. We expect the whole thing to go superconducting as soon as we hit the TC of niobium. That's exactly what happens. And notice that it goes superconducting around 9 Kelvin. So that tells us that there's nothing funny with niobium. There's nothing weird. It basically acts like a film of niobium. Right? We're not getting inverse proximity effect or anything like that. And then as we increase the island spacing, the transitions go to lower and lower temperatures, which is what you might expect. So it's a two-step transition, as you can see here, right? There's a T1 up here, one step here, and then there's another step there. Okay? And that's expected because the first transition is where the islands go superconducting, and then the resistance stays pretty constant as the coherence length of the gold increases, and then at this temperature, the coherence length of the gold equals a spacing between the islands become coupled, and the resistance drops to 0 across the array, which we call T2. So a two-step transition is expected. But the thing to note is that this is where individual islands go superconducting, and this is where the islands are coupled. Okay? So this should depend on just the islands, and this should depend on the island spacing. Okay? But if you look at the data again, you see that the island transitions themselves depend on the spacing. And that's weird. Okay? That's something that was unexpected in this data. In fact, I remember I showed this first time years ago, and it was just off the press. It was one of those things I had to give a talk at a conference, and I had nothing to talk about. My student took this data like 2 days prior, and I brought it in. I was so proud of it because it looked nice. And then someone said, why does T1 change with spacing? And I literally was like, I don't know. So anyway, that's unusual, right? That's something that we did not expect. So then we tested it more, right? Is it just that device? It turns out something we see all the time. We see it with regular thin niobium. We see it with thicker niobium. You can see if we increase the niobium thickness, the TC goes up more toward 9 Kelvin, but it still varies with spacing. And again, the island diameter is about 10 times coherence length. So you wouldn't expect any sort of suppression in this case. Okay? If you plot this, you can see that the transition temperature of the islands actually varies linearly with the island spacing. Right? We see this for all the different parameters. We put it with different types of gold and different types of niobium, put it for shorter island spacings and larger island spacings. And in all cases, you can see TC keeps getting suppressed, but it happens linearly with island spacing. So one takeaway from this that we realized is that if the transition temperature of the islands decreases linearly with island spacing, if you just extrapolate this line, you'll get to a point where at some finite spacing, the transition temperature is 0. Okay? And that means that even though the system is supposed to be superconducting at 0 temperature, right? The coherence length is supposed to be big enough that it's superconducting at 0 temperature, there's no transition, right? The transition is 0, which means that it's still metallic. Okay? So for these systems, as you increase the spacing, you're approaching a 0 temperature metallic state. So same thing here. So again, this system here, even though it has superconducting islands on it, as you march this point down, you basically reach 0 temperature for a finite spacing, which is an example of a 0 temperature metallic state. Okay. So that's one example of this sort of 0 temperature metallic state that you can see in these sort of phase-separated systems. Now, we can ask, what causes this approach, and basically, there have to be some sort of phase fluctuations on the islands, which is damped by a weak coupling between the islands, even though it's not coherent. And then at this point, you have coherent coupling between the islands as it transitions to actual superconducting state. So the takeaway here is that, for one, there's different types of correlations that can exist in phase-separated materials. There's strong correlations, or global couplings, which is what you get down here. And then there's something called we call regional couplings, which means that the islands are coupled, but not coherently. Okay? They're not coupled enough to have the same phase, but they're coupled enough to influence fluctuations on each other. Okay? And so for these sort of regional couplings, you can still influence their behavior. That's one takeaway. The other takeaway is that there's a finite resistance region that can persist as the temperature approaches 0, which may be one example of a 0 temperature metallic state. Now, this is as a very brief follow-up. I'm not going to get into any detail on this, but we've done many more studies on these individual islands, because one of the implications of this result is that superconductivity in the individual islands is suppressed, right? Otherwise, it wouldn't matter how coupled they are, right? If you have one island alone and its neighbor is infinitely far away, it has no TC, right? So that means you're suppressing superconductivity on the island. And we studied this more and found that the islands themselves are actually granular with crystals of niobium in them. And we discovered that this was another example of a sort of granular superconducting system where the TC basically depended only on the size of these grains in the island. And so this is an example of what we call rare grain superconductivity, where just the size of the largest grain determined the onset of TC. And this is interesting because it's related to a lot of other disordered or phase-separated systems where the onset of correlations is determined by the size of the largest region, or the largest grain in this case. And so that's what was causing suppression of superconductivity in our islands, and also what then coupled them together. Okay. So that was one example of using these island systems to look at finite resistance superconducting states. I'm going to somewhat briefly, talk about another example of looking at dissipative states, but in this case using intrinsic dissipation in superconductors due to magnetic fields, which is magnetic vortices. So, just to be clear, we talk about vortices. You guys had a polar vortex here last year too, right? We were super cold. We had -40 in Illinois. It was actually where we were actually colder than you, I think. So we're not talking about a polar vortex. We're actually talking about magnetic vortices here. This is the prettiest picture of magnetic vortex that I could find. We can just pause here for a second and relax while we look at it. This is to motivate the whole discussion of vortices because they're beautiful, as you can see. Okay, so what is this? Okay, I don't know what this is, but we're talking about something that has an analog to this, which is basically an excitation of a superconductor. Okay, an excitation of a superconductor is dissipative, so that's relevant, right? And the excitation is a magnetic field penetrating, right, with a flux quantum through a superconductor, and to shield it from the rest of the superconductor, there's a circulating current, supercurrent going around it. Okay, so in thin film superconductors, magnetic field penetrates its vortices. One vortex has a circulating supercurrent that contains one flux quantum. Okay, and that's a vortex in a superconductor. And most of the time it's shown with more boring pictures like this. That's what it usually looks like. It's just a vortex where you can see the amplitude of the order parameter goes to 0 right there because it's a phase slip basically, right? So the phase slip, it loses phase coherence right there, and even normal core in the superconductor. And vortices have repulsive interactions. They can form a lattice in the superconductor, which is also why we look at them. Okay, so why is a vortex dissipative? A vortex is dissipative basically because of a Magnus force. It's a circulating current, right? Sort of in the same way that tornadoes move, I guess, right? So it's a circulating current. So the current provides a Magnus force, right, which is like a B cross I. You can use a right-hand rule on this thing. That causes the vortex to move. The vortex crosses the sample, and because it basically acts as a phase slip, you get a phase slip across a superconductor, which produces a voltage, right? You change a phase across a superconductor, you get a voltage, and that's what leads to an applied current giving you a voltage. That's what you measure as a resistance. Just to be clear, it's not the normal electrons in the vortex core that leads to resistance. It's really driving this thing and getting this phase slip, which leads to a resistive state. But it is still dissipative. You get resistance when you measure this in a superconductor. Okay, and why do we care about vortices? Well, we care about vortices for the same reason we care about superconductors. We want something that's zero resistance. Vortices prevent it from being zero resistance. And so, if you want to have a detector or wires or have large current density in a magnet, for example, achieve the highest magnetic fields, the biggest challenge is understanding how the vortices penetrate, right? The reason that MRI magnet wire is limited the way it is because vortices start penetrating into the wire itself. Okay, so understanding and controlling vortices is key to really achieving the best superconductivity. And vortices have just been studied for many years. They're very interesting because they interact in superconductors. They have lots of phases. As I mentioned, this phase diagram for the 2016 Nobel Prize was a vortex phase diagram for 2D superconductors. There's lots of open questions about how does a vortex lattice form? Is it glassy? Is it liquid? How does it melt? What goes on? There's been lots of interest in this over the years, and even there's also interest in driving vortices and instabilities. There's something on dynamic instabilities. This was a recent paper showing that that you get a Mott insulator to metal transition as you drive vortices out of an array, just like what we study. So there's a lot of interest in seeing new physics and interactions in these sort of systems. Okay, so there's an opportunity to understand things like the role of dissipation, the role of interactions, and any sort of new dynamics that might appear. And just to note, when I'm talking about the vortices, we're actually measuring in the superconducting regime. So before I was talking about up here on this phase diagram, now we're looking in the region where it's really superconducting and then applying a magnetic field, just to differentiate. And for people, right, so here, it's superconducting at zero field. And for people who care, it really acts like a Koslitz-Thouless type system here. It's a real 2D system where we've looked at how the exponents change for the IV curves. Okay, so why am I talking about vortices for these systems? Well, just like before, we have this well-controlled island array, and the well-controlled island array allows us to have well-controlled vortices, right? It's another way of controlling the dissipation in the system. And that's because vortices are a phase slip, and so they occur at the weakest point in the junction, which in this case is the space right between the islands. So here, if we have our superconducting array, right, with islands and a space between them, if we apply a magnetic field, the vortex will pin between the islands at the weakest point, okay? So if we have superconducting islands, here's a triangular array of islands, the vortices will pin right in between where the islands are, which is the weakest point, and they penetrate all the way through. And so the array is basically a periodic potential for the vortices, where vortex propulsion makes the vortices arrange themselves into the lattice between the islands. Okay, so it's another picture. I don't know, this is not as, okay, whatever. The red dots are vortices. They're in the lattice. Okay, but this is more interesting. So when they arrange themselves, they actually arrange themselves in an interesting sort of array, which means that, imagine if I have a square lattice and I apply just enough magnetic field that I can have one vortex in every other lattice point between my islands. Okay, that's a function of field. So if I take my magnetic field and divide it by, the number of flux quanta, I get to 1/2. Okay, and that's something like this. And so we call this a frustration of 1/2. It's the amount of flux per flux quanta. Okay, and if it's a 1/2, it means that we have a flux quanta in every other plaquette. Okay, if it's 1/3, it means we have a flux quanta in every third plaquette. If it's 2/5, it means we have a flux quanta in 2 out of 5 plaquettes, and they arrange themselves into a lattice, right? But this is interesting because vortices are interacting. When they arrange themselves into a lattice, they pin. Okay, so if I'm measuring resistance, what I expect is that when I have a commensurate lattice, which is some rational integer of n over m, that I have lower resistance. When it's non-commensurate, I have higher resistance. Right? And so then I just measure resistance as a function of field for this sort of system, and I get data that looks like this. So this is resistance. And here's I've actually put it in terms of frustration. Remember, this is just my field value, but my field value where here I have one vortex filling every plaquette between the islands. And notice what you see. At zero field, it's a dip. There's zero resistance, right? And then as I go away from zero field, my resistance increases. But then as I go to quarter filling, it decreases again, because my vortices are interacting, so they're pinned. Then my resistance increases, and then, I don't know, this is like 2/5 or something. I get these little dips in between, and then at half filling, I get a very strong pinning again, so my resistance goes down. Same thing at 3/4. And then kind of miraculously, I've increased field here, right? My field at this point is bigger than my field at this point, and yet I have a lower resistance there because at one vortex for every plaquette, I have such a strong lattice that it's strongly pinned. And so this is really a way to control resistance in a superconductor. By pinning vortices and understanding their pinning and depinning behavior, you're really controlling the dissipative states. And it really, I think, beautifully illustrates that. Now, this is as a function of temperature. So all I'm doing here is increasing temperature and showing how vortices get thermally excited at these pinning sites. But the really interesting physics, I think, happens when you drive it with a current. Okay, so temperature just excites it out, but if you drive it with a current, then you can force dynamics of dissipative and non-dissipative states, and that's what we focus on. Okay, so this is exact same data, except here, instead of having temperature, I'm driving it with a current. Okay, so if you remember before, this is frustration. It's only going up to half filling right now, but you can see basically, you know, for low currents, it's superconducting, and then at a quarter filling, I get a little dip, and at a half filling, it's superconducting. So same thing here, right? So I get a dip at a quarter filling, and I get a dip at half filling. It's very similar, except there's a lot more going on here. Okay, so what's going on in this region? You can see that first I pointed out this flux flow line. This is basically where I have individual vortices being pushed out of the lattice, and they just start flowing. So this is where my resistance is just proportional to my magnetic field. This is kind of the boring, non-interacting vortex case. Okay? But if this is the boring, non-interacting vortex line, then all of this is a really interesting correlated interacting vortex line where everything's working together and creating all this other sorts of structures and behaviors. And so this is the region we focus on. So you can see a couple things. Like I said, you can see the pinning at commensurate vortex lattices. Right? Here's at a quarter, here's at a half. Okay? You can see at a half filling, you get this dip to peak behavior. That's something pretty interesting because you're just increasing current, and it goes directly from a superconducting dip to a peak in resistance, which has been associated as a Mott-insulator transition before. Notice you see something different at a quarter filling. At a quarter filling, it has a dip, but it kind of waves around before it gets to the peak. So it's unclear. The interactions are weaker here, and so you don't get quite the same behavior, and it actually moves in a different way, which is something that hasn't been studied before. The other thing that we noticed is that at incommensurate fillings, like 0.22 and 0.43, you get something that looks like it increases, and then suddenly the lines start bunching up. You see that bunching up of lines here, and the same thing here, you get a bunching up of lines. And so that was something interesting to us. It tells us how does the lattice respond when you apply a current, and why would it lead to this sort of bunching up of lines? And so in this case, we want to know how does the state depin, and does it melt like a glass? Are individual vortices continuously depinning? What we find is that this looks like a two-step transition, basically, where the first step is here, and then the things bunch up, and you get a flat region there. What we think is happening is that we're going from an incommensurate filling state here, and then individual vortices leave. So individual vortices depin, and then leave behind the lattice. And this is interesting. So we didn't know if this tells us that it's not that all the vortices just depin at once, nor does the whole thing depin, but it's a polycrystalline lattice where individual vortices leave, then they leave behind a commensurate filling where nothing happens for some time, the resistance is constant, and then at the second step, all the vortices leave, and we end up in a just a vortex flow state. And so for us, this was interesting because it gives us some new understanding of how this sort of interacting lattice can lead to a polycrystalline and not glassy state, and also how it melts. Okay, so I'm just going to show one more slide, or two more slides, and this is just as an example of how these sort of island arrays are interesting and give you insight into different sorts of systems. And so I'm going to end with just two slides on a topological insulator, because I said I'd lead to this. But for people who know about topological insulators, these are materials that are supposed to have spin momentum locked states on their surface, which means that if you put a current in one direction, you should have your spin aligned in that direction. The current in the other direction has spin aligned in the other direction. Okay, so this might be interesting to look at vortex dynamics. You can imagine putting a vortex through, which forces your spin to go in one way, and then how does that affect how the vortices depin? Okay, and so we end up putting these islands on a flake of bismuth solenoid. Here's the bismuth solenoid. Here's what we put on here. There we go, niobium titanium islands, mostly on there. And you can see we get all these same behaviors for the topological material. We get superconducting transitions across the system. We see frustration effects across the system. And so you can see all the similar vortex things, but now in a topological material. And we can look at dissipative effects of when the vortices unpin. And what the critical current of the array looks like. And just to note, what we see are these very strong asymmetries. So here's the red curve is when we have a negative field, right? You can see for negative field, we get a very small peak here that goes into a high peak for positive current. And then if we have a positive field, we have a small peak for negative current and a small peak for positive current and a high peak for negative current. And so on the topological material, something we don't see in other materials is an asymmetry between the direction of the field and the direction of the current. They seem to be correlated, and when we get peaks, and how high the critical current is, which tells you that pinning and depinning are somehow influenced by dissipation in the topological surface, which is consistent with this sort of surface spin momentum locking. And same thing, you can see we get different types of dissipation. If you measure the width of your critical current, you get different values depending on whether you have positive or negative field or current values. Okay, so hopefully that's giving you a sense of dissipation in superconductors, why it's interesting. I think that this is really an ongoing challenge in condensed matter physics in general, not just in superconductors, but in all sorts of disordered correlated systems. We talked about how controlling dissipation via normal metal channels leads to these metallic superconducting states. I mentioned briefly about this rare grain superconductivity, and also talked about controlling dissipation with vortices, how that leads to new interacting vortex regimes, and we can really sometimes see the influence of different sorts of materials on dissipation. And for us, this is relevant not just to superconductors, but really to a variety of correlated and phase-separated systems. Okay, so thank my group who worked on this, some of our collaborators on this, and also the DoD and the NSF for support. So thank you very much.
Any question from audience?
For the topological case, there was an interesting little island so you have the IDV is 0 in the middle.
This?
And yeah, and on both field orientations, you have a little island on the left-hand side, sorry. That plot near DIDV equals 0 in the middle.
That?
That, which shows up on both sides.
Yep.
I've recently been talking to people who are excited about reentrant superconductivity, where superconductivity is destroyed and brought back by the same thing.
Right.
Do you have any ideas? Is it sort of leaving superconductivity and coming back, or does that, as current is increased, or do you know what that might represent? What this feature might?
I'm trying to remember. My immediate answer is no. I don't know what it represents. This is honestly sort of this is data that we're still thinking about. It's relatively new. No, I don't remember. I mean, also I should mention that some of these features outside are also reproducible and are different on either sides, and we don't. I usually associate these sort of things with multiple and brave reflections or something, but it's a pretty,
The
geometry is different, and also the other weird thing besides that is that look, why would the critical current be so high? So this is a high peak, but it's suppressed, right? And then this is a low peak, but not suppressed, and then this one has a little bump on it, which, like you said, looks like some sort of reentrant superconductivity, and the other one doesn't. So I don't know what that is the short answer. Yeah.
Any other question? I have one actually. So what is the reason that you go from 1 flux, 1/2, and 1/4? Because this is like a triangular lattice, right?
Yeah.
Why should it not go 1/3?
Was it a triangular lattice?
It's a triangular lattice.
So why
Yeah,
should
so that's weird.
Well, we do. I mean, what do we not see the other fractions?
That's
Yeah,
a
1/3, for example.
We do.
You're
see
finding
that.
a Hofstadter spectrum rather than a Wannier spectrum.
Yeah.
So we do see the other ones, but they're weaker for whatever reason. So this is a third.
So, like
So we can see that. So you can see this one right here is a third,
Right.
and that's a third.
But the main
Well, a
one
third
is
shows
1/3.
up in a square lattice also,
Yeah,
but a quarter doesn't. Okay.
it's square.
In a square lattice.
This is triangular lattice.
What?
These are triangular lattices.
I know. So,
Yeah.
sorry, in a
Yeah,
triangular
triangular
lattice,
lattice.
a quarter doesn't show up.
Yes, sir.
Actually, a third does, but not a quarter. I think you don't have good commensurability. Third with triangular and what?
I don't know. We see it.
I know.
Clearly.
It's strange, right?
Exactly.
I
I mean, you drew it right for square lattice.
I know we drew. Well, I stole that picture from Zara, but yeah, but we do get. It is weird. I agree, because it's not clear exactly how they're arranging themselves and why it should be so strong. But
But there is this classical, I guess, these chaotic orbits
Yeah.
in antidots, like with electrons, right? So then it goes with exact that kind of thing. But maybe this is
Yeah.
more complicated or more interesting that they don't show up the same.
yeah, I don't know. I mean, the other thing is the size of the vortices is the size of the vortices is relatively big, right? So the vortices are bigger than the spacing between in some sense bigger than the spacing between the lattice, right? Even though they're repulsive, they should cover multiple lattice sites. So I don't know if that matters at all for
Sure,
how they
but the
arrange
main
it.
effect it has, as you said,
Yeah.
is on changing the phase of your islands.
Right. That's right.
Right.
That's
That's
right.
how- whether that
That's right.
is coherent or not.
Yeah.
That's right.
Interesting. And the interesting thing is here, when you change temperature,
Yeah.
a quarter stays the same way as a dip, or a half, any of them.
Yeah.
Whereas when you change current, instead,
Yeah.
you're getting this inversion.
Or at a half, you mean?
Yeah, in that a dip
Yeah, yeah,
becomes
yeah.
a peak.
Well, because in one case you're driving it, so I mean that's why
Yeah,
it was
that's
interesting
exactly
that it's
right.
assumed
Yeah,
that you're
yeah,
both
that's why it's
depinning it, and that's why the
interesting.
current-driven ones are
Right.
interesting,
Yeah.
and that's why I was saying I think it's also interesting that even a quarter and a half don't even act the same way when you depin them, which you might think it would if they were but yeah, so
But actually, a follow-up on that, like if the vortex is bigger than the islands, right? When you want to move them, they have to deep in and move. And
Right.
it's,
but they clearly do, right?
Yeah.
I mean the thing is that they clearly so. What's interesting, we do see standard flux flow behavior, especially like for the high currents, you just see flux flow. I mean, until you get to some large
everything is
field value, right? It's just, but even that starts peeling off
Mhm.
at a high enough field value, right? Especially when you go towards this.
So what is the resistance if you want to convert the 9 microamp to a voltage?
Oh, I don't remember exactly. Yeah, I don't remember. I'm sorry.
Okay.
Yeah.
Thanks.
But across the array itself has resistance of the scale of kilo ohm or something like that.
All of this is you're at low temperature.
These are at low temperature.
So what happens if you go between your T1 and T2 as a function of field? When supposedly, right,
Yeah.
it's just the islands themselves.
Well, we don't see this sort of commensuration. Is that what you mean? I mean, it's not
Yeah, that's what I
superconducting
know.
there, right?
You don't see anything.
No,
you don't
it's
see
no, it's
anything
not.
at commensurability.
No, because the resistance is still relatively. I don't have the thing, but the resistance. I mean, the resistance is high here. Right? It's not.
Yeah, but you can measure the five,
But we
six
but we
places.
don't see
Okay.
that. Yeah, we don't see that in this regime. We don't see any commensurability at all. Yeah, not until we're pretty deep into this. I mean, and you can even you can see it. I mean, this is a function of temperature, right? And so you can actually. Right. I mean, it looks. Oops. It looks like you just get. I mean, this isn't even the transition temperature. The transition temperature would be somewhat higher, but even as you get to 800 millikelvin, you start losing all the features, right? You don't even see the dip at 1 anymore. So this is as close as we get to that region.
So if you had something that looked like a Sierpinski gasket,
I don't know
does
what
that?
Sierpinski gas
Huh?
is. I don't know what that is.
It's a,
It's a fractal.
it's a yeah. In that case,
Decimated
in that
triangles.
case, I'll
Okay.
forget it. How about okay? In
I
that
mean,
case,
we've looked at different structures of arrays. I mean, if that's
right,
what you're
yeah,
asking.
Well, what I was the idea of a fractal array would be then that you would have go from having one step to having a series of steps as regions of different scales
Yeah.
go superconducting.
Yeah.
But I'll flip it around now. So if you have instead like a quasi-periodic lattice,
Yeah.
does that mean that instead of having rational numbers, you'd end up seeing rational approximates of the golden ratio or something like that?
We have not. So we've looked at this as a function of disorder somewhat, like just point disorder on the things, and it's to first order it just tends to smear out a little bit. We've also tried to do interesting like phyllotaxis spiral structures and stuff, but those end up approximating square lattices, and so we just see square lattices. And then we've also tried, what, like you said, the correlated disorders. So basically, the lattice size changes, as you mentioned, just continuously across the thing. But that also, it just kind of smears it out a little bit. It doesn't, at least to first order, it did. Yeah, it was hard to. We haven't gone into a lot of detail in studying these, but for sadly, most of the interesting patterns we've tried have been not very interesting, at least in terms of features we can.
A lot of work for not too much groovy.
Yeah, kind of. Yeah, I mean, but I mean, these aren't that hard to make, and so we're totally interested in looking at if there are interesting patterns that don't end up just reverting to a square lattice, then we're interested in seeing that.
Any question? Okay, if not, let's thank Nadya again. So we're going to go upstairs.
Thank you.
Upstairs?
Oh, okay. Oh, okay. Okay, perfect. That's perfect. I can leave my stuff in our office, or just bring it with me for now?
The last minute. Okay. We can do that.